Hello, YouTube! Today we're going to be talking about Newton's third and final law of the force laws. Newton did a lot of stuff, including inventing a lot of stuff. I don't know. Very busy person. Um, I just sidetracked myself. In particular, today we're talking about the way that things push each other and pull each other. So we've talked a bit about what forces do. We've talked a bit about how to actually calculate out what the force is going to do. And now we're going to be talking about um, where those forces are coming from a little bit, and in particular how they're like coming from different objects and how those objects affect each other. So, in particular, if you are able to describe the force on objects on each other using Newton's third law, that's perfect. The ways you're going to do that are by naming and labeling action-reaction pairs. In particular, what I want you to focus on is how to figure out what is not an action-reaction pair. Because if you have an action-reaction pair, it actually means something very specific, and some other things might accidentally look like action-reaction pairs and not be, which does actually have some pretty significant implications. And then the last one is if you know that two things are pushing each other, you should be able to calculate the acceleration of one of them using the acceleration of the other. And there are actually multiple ways to do this, but we'll focus on using Newton's third law to do it today. So, Newton's third law is words-wise a little simpler than the other ones, so I didn't really break it down the same way. And it's that for every action, force, there is an equal and opposite reaction, also a force. Opposite is referring to the direction, by the way, on the object that made the original force. So pretty much this is just saying that anytime you push something, you will get pushed back with the exact same amount of force. This is always true. It doesn't matter if the thing moves. It doesn't matter if you move. It doesn't matter if one moves but the other one doesn't. It doesn't matter if one of the things breaks. The amount the two things are pushing each other is always going to be the same. This is pretty counterintuitive because you assume that if you push something and it moves but you don't, that means that it got pushed harder than you did. But the problem with that is that you're basically assuming that the only thing that's doing the pushing on either of those two is the thing that is being, or sorry, that there's only one force on either of those from that one thing. Not going to be the case every time. One of the other things that's weird about this is, as well, is that if the force is the same but the mass is really different, the acceleration is going to be really different because F equals ma. And that also ties in with our whole idea that if the object's got less mass, it's harder to accelerate, or sorry, easier to accelerate. So if one of the two objects that's being pushed when the two push each other has less mass, it'll accelerate more even though the force is the same. And there's one other thing that's a little weird about this that for me was always the big misconception. So like for me, when I heard this, I was like, okay, well, if every force is going to make another force in the opposite direction, doesn't that mean they'll just balance out and nothing will ever accelerate? And this took me literal years to figure out why that doesn't work. And the big thing is that it's talking about two different objects. So basically what this law is saying is that if I have two people pushing each other and or like a person pushing a wall, there's going to be some force from the wall on the person. So this is our person, this is our wall. There's also going to be some force from the person on the wall. And those two things are going to be paired, meaning they're the exact same size, always, no matter what, forever. What's important about this is that these are showing you two different objects. The object on the left can't be balanced because the force is going to the left. There's only one force. The object on the right can't be balanced because the force is going to the right. There's only one force. An example of something like this making it so you wouldn't move because the action-reaction pair are balanced are if you try to take your chair, and you take your hands, and you try to lift yourself up on your chair. You won't be able to do it just by pulling up. And that's because when you try to pull yourself up, you also push yourself down by the same amount. And in that case, yes, the forces will be balanced because in that case, the force of you on yourself will be the same as the force of yourself on you going in opposite directions on the same object. And because it's the same object, those two balance out and stop it from ever moving. Or, sorry, stop it from ever accelerating, which some subsection of that will be moving. So doing a few examples of like how this factors into some stuff, we're going to talk about holding up a book, then we're going to talk about pushing a bunch of boxes that are connected to each other, and then we're going to talk about tug of war. And so unit 2.5 Newton's third. We've got, first up, holding a book. So if I've got a book in my hand, I suppose I can put a book in my hand. Then let's look at the forces on my hand, and let's look at the forces on my book. The book is going to experience a force of gravity on the book going down, which will be the mass of the book times gravity. It's also touching my hand, and so because it's touching it and not falling through it, there should be a normal force going up. Now the book was staying at rest, which means the net force is 0. That tells you that those two things have to be balanced out. That doesn't mean they're a Newton's third law pair. The pair for the normal force, the trick for this is to think about where these forces are coming from. Where does the force on the book come from? Well, it comes from my hand. This is the normal force of my hand on the book. This is the second time I've used this convention, so I do want to explain it. When you're labeling forces, the subscripts are going to be the force of the first object on the second object. So just add the word on there. If you're drawing a free body diagram for the book, B will always be second. However, if we're drawing the free body diagrams for the hand, my hand is getting pushed by my body up, so the force of my body on my hand goes up, and the force of, let's say arm instead. I just realized a problem with how I labeled things. The force of the book on my hand goes down. These two are an action-reaction pair. The force of my hand on the book will be the same as the force of my book on the book on my hand. Always. So again, the normal force and gravity will never be an action-reaction pair because they're not the same type of force, they're on the same object, and they're coming from different things. So what is the reaction to the force of the book on gravity on the book? Well, I would need to draw the thing that's making the force of gravity on the book, which is the Earth. When the Earth pulls the book down, the Earth also gets pulled up by the book. The amount it gets pulled up will be the exact same. Now, because the mass of the Earth is so insanely small, and because the book is connected to me, which is connected to the Earth, and by the book, the amount that the Earth pushes me up with normal force is the same as the amount that I push it down, so they wind up canceling. This is the real reason why it doesn't move. But the reason it doesn't look like the Earth is moving, even though the Earth is getting pulled up, and it's got this unbalanced force, it's not unbalanced, there's something else balancing it, but even if it was unbalanced, the reason why it doesn't seem to be accelerating is because the Earth is 10 to the 23rd, roughly, times more massive than the book, which means that the acceleration will be 10 to the 23rd times less than the book. For reference, 10 to the 23rd means that the acceleration of the Earth, 1, 2, 3, 1, 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 there is going to be about this big. For reference, being able to see this level of acceleration or motion is about as difficult as being able to stand on the Earth, look at the sun, and find a needle on the surface of the sun. It's not gonna happen. So let's draw a free body diagram and label our pairs for a second example of if we've got a bunch of boxes that are pushing each other. So we've got box 1, we've got box 2, and we've got box 3. And let's say that box 1, 3, let's actually go this direction, is getting pushed to the left by a person. So if I were to try to draw out all the free body diagram for all these boxes, we'd have box 1, which we're going to need a dot, we're going to need mg, we're going to need the normal force on box 1. Those two, again, are not a pair. The normal force is coming from the floor. The pair for the normal force would be the force on the floor going down from the box. Box 2 is pushing box 1 to the left. So I need a force from box 2 on box 1. Nothing is touching box 1 pushing it to the right, so there's no force going to the right. Something I want to highlight about this. Box 3 is not pushing box 1. The person is not pushing box 1. Box 3, you could make an argument, is indirectly pushing box 1, but because box 3 is not touching box 1 is not being pushed by box 3. Only draw forces for things that are touching it, because other things will be indirectly like causing a force. Direct forces are the only thing that go on a free body diagram, and the only thing that determines the acceleration. So if we're doing box 2, now what we'll have is a force, because box 2 is trying to smush through box 1, box 1 will push it back just as hard. So this will be the force from box 1 on box 2. These two, you'll notice box 1, 2, 2, 1. See how it's just the same letters but flipped because it's one on the other and then the other on that one? Those two are a pair. So that's our first pair here. Additionally, box 3 is pushing box 2, and the size will actually have to be a bit bigger because it's all accelerating to the left. So we'll have the force of box 3 on box 2 going to the left. Still going to have gravity. Still going to have normal force. For box 3, we have this person pushing it to the left. And we have box 2, which is trying to smush through, saying, hey, please stop, and pushing it to the right. These two forces, 2, 3, and 3, 2, are also a Newton's second law pair. So again, these ones are pairs, and it's pretty easy to see when you've labeled it out like this because you've got 2, 3, and 3, 2. The last example I want to talk about before we do an example with a bunch of math is tug of war. So this is an example where you've got things accelerating. So we've got two people pulling on a rope, person 1 and person 2, and they're connected by this rope. The rope is going to pull person 1 to the right, with the force of person 2 on person 1. Force of person 2 is going to be pulling to the left. Force of person 1 on person 2. And what should be happening here is if these two people were, for example, on ice, they would just come smashing in towards each other and then right in the middle. This is a Newton's third law pair. These two are always, always, always the exact same as each other. So then the question is, why doesn't that happen? And why does one of them accelerate in a direction and bring the other one with them? And the answer for that is friction. Whichever one is winning will have a greater force of friction. So if the force of friction on person 2 is bigger than the force of friction on person 1, then the unit will accelerate to the right because overall there's more force going to the right than there is to the left for each of these cases. And so this is actually a big part of why, typically speaking, if you have a tug of war, just whichever side is heavier is going to win, because for reasons we'll get into later, whichever side is heavier winds up having more normal force, more friction available. All right. As far as naming action-reaction pairs and like using vocab to describe it, oftentimes something that'll wind up happening is it'll be like first object verbs second object in a direction. the reaction to that would be that the second object does the same verb back to the first object in the opposite direction. So for example, and what I really want to highlight about this, it's the same type of force every single time. I push the ground down with a normal force. When I do that, the ground pushes me back up with a normal force. And if the block pushes the wall will push the block back the other way the exact same amount. In particular, I did already say this, but just re-highlighting, F12 means the force of object 1 on object 2. A couple YouTube videos. The first one is the same series with the space, where you get to see how Newton's third law applies in space, so that it's a little more intuitive, so you can actually watch it happening. And then the second one is a video that's talking a little bit about the way that the Earth and the Moon pull each other and how those two things are the exact same, even if that feels a little counterintuitive. Let's do an example with some math and then call it. So, we've got a 10 kilogram cat, and we've got a 20 kilogram dog. And we know that the acceleration of the cat is 5 meters per second squared. And as I've drawn that, that's to the left. If you wanted to make it to the right, totally fine. A, we're supposed to find the net force on the cat. B, we're supposed to find the net force on the dog. And C, we're supposed to find the acceleration of the dog. As a heads up, in the future, if you were to see this problem, it would probably skip straight to part C, and you would have to realize that you need to do part A and B first in order to get C on your own. So, finding the net force on the cat. Well, we don't know a lot of equations so far. And there are forces involved, so free body diagram? We're going to need one for each object. So if there's 2 objects, we'll need 2 free body diagrams. One for the cat, one for the dog. The cat's going to have some gravity and normal force on it. Make sure I use the mass for the cat. And it's also going to have the force of the dog on the cat. The dog is going to have the force of the cat on the dog, the mass of the dog times gravity, and the normal force on the dog. So just looking at this, something that jumps out to me is that the normal force and gravity are probably balanced, and that each of these only has one force acting on it. And also we see DC, CD. These two are a pair, which we might have to come back to later. For now, let's just start thinking about the cat. Well, our only equation we really know is that net force is equal to mass times acceleration. If I want to do it for the cat, I'm just going to go ahead and pop subscripts on all of this. The force on the cat is equal to the mass of the cat times the acceleration of the cat. In this case, actually getting ahead of myself, I know mass of the cat, I know the acceleration of the cat. Nice and easy, we can just go ahead and do it. The mass of the cat is 10 kilograms. The acceleration of the cat is 5 meters per second squared backwards. So I'm going to go ahead and tack a negative onto that. Multiplying those two out, I've got negative 50 newtons is my net force on my cat. If I come back to my diagram, hopefully you can see that the only force on the cat is the force of the dog on the cat. And so that means that this arrow has a size of 50 newtons because the net force is the only force in this case. That's interesting because that means that these two being paired have to be the exact same as each other. And this is going to get into how we do B. The net force on the cat is equal to the force of the dog. Let me do it this way. Is equal to the force of the dog on the cat. But because of Newton's third law, the force of the dog on the cat needs to be equal to the negative force of the cat on the dog. They're the same size, but their sign is flipped. Well, the force of the cat on the dog is just the force on the dog. But, again, got to be careful with that negative. Because that's the only force on the dog. So, taking all that and chaining it together, I can just say that whatever my net force on the cat was, that'll be the same as the net force on the dog, but negative. So the net force on the dog is negative 50 newtons. And that's really useful because using that same equation of net force, this time for the dog, on the dog is equal to the mass of the dog times the acceleration of the dog, I can find, I don't know why my nose got so itchy, the acceleration of the dog just by dividing each side by the mass. So my final answer will be that my acceleration for my dog is equal to the force on the dog divided by the mass of the dog, which will be 50 divided by 20, which gives us 2.5. Before we call it quits, there is something I want to highlight here. If you look at the acceleration ratio between the dog and the cat is accelerating twice as much as the dog and has half the mass. The acceleration ratio will be flipped from the mass ratio. And you can figure that out by plugging in for mass over acceleration on both of these. And if you divide the two, you'll have dog over cat equals cat over dog, which means that, again, their mass and acceleration ratios need to be flipped from each other. And that's a little bit of a shortcut that you could use to solve this one. All right. That's it. Thanks for watching, and goodbye, YouTube.